Today we're going to look at an audio output power stage. We often would like to drive a very low resistance with an amplifier. And this is because a quality speaker has an impedance or a resistance that's approximately somewhere between 4 ohms and 10 ohms, depending upon how good the speaker is, how big the speaker is, and the mechanisms that are internal to the speaker. We could try to do this using an op amp. So let's say that we configured an operational amplifier in the unity gain configuration. And that amplifier is going to drive an 8 ohm resistance. Let's further say that this operational amplifier has supply rails of plus 9 volts and minus 9 volts. Ideally, if we put in an input signal that swung between plus and minus 9 volts, at the output we would have a voltage swing between plus and minus 9 volts. And what does this mean for the peak current that the amplifier must be able to supply? Well, if we look at peak current, we'll call this I max. It would be equal to the peak voltage divided by the resistance, or 9 divided by 8. And this is greater than 1 amp. I min would be the minimum voltage divided by the resistance, or minus 9 over 8, less than minus 1 amp. These numbers are too big for most amplifiers. Most operational amplifiers will limit the maximum current that they can supply to a load to somewhere in the tens of milliamp range. And this means that we must come up with some way to drive this speaker, so we need an output stage. The simplest output stage is a Class B stage. In a Class B stage, we will take 2 transistors that are configured as emitter followers, and have these transistors provide the current for our speaker. And let's again say that our speaker is 8 ohms. Now, we don't need to know how an emitter follower actually works. All that we need to know is that the input of the gain of this amplifier from input to output is approximately unity. In other words, whatever goes in at the input comes out of the output. The problem that we have is that this output stage requires that the voltage across the base terminal to the emitter terminal be greater than 0.7 volts for the NMOS and less than negative 0.7 volts for the NPN and less than minus 0.7 volts for the PNP transistor. Now if we use that same operational amplifier in a unity gain configuration, this is our input now. So we're going to drive the transistors with a unity gain operational amplifier, and the transistors will drive the 8 ohm resistance. Now if we plot our input waveform, it might be sinusoidal. And let's note on here plus 0.7 volts and minus 0.7 volts. Now these two transistors won't turn on until the input, which is equal to the value at node A here, is greater than 0.7 to turn Q1 on, or less than minus 0.7 to turn Q2 on. So if we were to plot our output waveform, it would look something like this. The output's off until the input goes above 0.7 volts. Then it follows the input. Then it cuts off again. Until the output goes below 0.7. Then it follows the input again. And we repeat. So our output looks like a sinusoid except for these regions where neither transistor is on, and this is called crossover distortion. As the current is crossing over between Q1 and Q2, or between Q2 and Q1, we get this crossover. This will cause distortion in the sound, or poor sound quality. In order to fix that, we're going to close a negative feedback loop around the two transistors. So we'll draw our same configuration. We'll still have our operational amplifier. Configured in a unity gain mode, only this time we're going to take our feedback from the output of the amplifier and tie it back to the inverting terminal of the operational amplifier, like so. Now we still have Q1 and Q2. Let's examine the input now. So we're going to place a sinusoidal input at the input. To pretend that I can draw a good sinusoid. It looks something like this. Now what happens, we'll draw our same 0.7 and minus 0.7 regions. Now what happens is when the input is less than 0.7, these two transistors are turned off. And when they're turned off, the feedback loop is not closed around the operational amplifier. So what happens is any small perturbation in the input causes a large perturbation at node A. this large perturbation at node A turns transistor Q1 on, for instance, if it's positive going. So now what we would see is a smaller period where there's distortion due to crossover. Then the output would follow the input. We'd have a smaller period of disruptance in that crossover region, and then the output would follow the input. The result would be that our output waveform, the blue waveform that I'm drawing here, is a lot closer to the original input waveform. You have to pretend again that I'm an artist, but you should be assuming that the blue waveform I'm drawing is identical to the red waveform that was put in at the input. So to recap, when the input signal is below 0.7 but positive going, the feedback loop is broken, causing the gain of the loop to be equal to the op-amp's voltage gain, which is very large. This causes small perturbation in N, causes a large increase in the voltage level at A until transistor Q1 turns on and closes the loop, and then the output simply follows the input. We will be building a Class AB amplifier with a couple of modifications to improve linearity tomorrow.